hello guys, and welcome back to this one again. And exciting time. I think we've spent the last four parts, trying to understand the brute force and how what makes it tick, helping understand the helper functions, and then basically coming around to the final function. And as we approach this final function, or basically the function that gives us the time of n squared and space O of n, we went through a lot of helper functions. But now we're going to be looking at the optimized code and seeing how we could, rather than go n square and be checking height and all that good stuff, right? We could in one fell swoop also get that same optimization, or basically check if a list is balanced. Now let's see how we do that. Now let's look again at what a balanced list is. Now we went through this and we basically said the rule or the invariant for a balanced list is basically when a list, right, has a difference greater than -1 in the node sorry, greater than or less than or equals to 1, right? So you see 2 minus 0 is going to give us what? 2. 2 minus 1 is going to give us what? 1. So basically the length or the difference in height between this node, or basically all nodes in that tree, should give us a height difference less than or equals to 1. And basically this one is not doing that. So anywhere we find that when we check out all the nodes, we don't find that difference consistent to be less than or equal to 1, then we know that we are missing out we are speaking out in balance. And that's what we try to adopt here, because immediately here you notice that we do a post order transversal. Now what's a post order transversal? We go to the left, we go to the right before then trying to analyze the specific node where we find ourselves. So let's try to just give that a physical representation. Now let's say we are trying to analyze this node over here. A post order will first go to the left node and try to analyze it, go to the right node, try to analyze it, and then before coming back here to finally do the final analysis and return the result. And that's what we see here. Now basically what happens here is that we call this balance up on the left node, and we also go ahead to call on the right node, and we hold our values, and then we go ahead to try to find the height of this node based on the values returned from this is balance up operation that we have just run. So ideally our is balance operation returns us a tuple of the height of the tree plus a Boolean value saying either true or false for the balance, if that node is balanced or not. We are doing a node basically investigation, a node based investigation for all nodes. Now we check for height. Height is our normal is it convict or suspect, where we say 1 plus max of the left node and the right node to find the height of a value. So we've gone through this before, right? And then what we do is that when we return that tuple, we now check if that node returns a true or a true, but in this case basically it checks if it returns a false. If not, because we said if not this node index of 1, so basically if it is not true here and true here again for the left and the right node, then we are going to go ahead to return the height we found for that node and false as well up the stack, because this is a recursive stack, right? And then we go ahead to say ABS balanced equals to ABS left. So absolute, we should do an absolute check to see if our table is balanced, or our node, that specific node we are dealing with, is balanced. How do we do that? So we take the left node and its height, right, minus the right node and its height, and see if it has a height difference less than or equals to 1. If it does, then we return a positive for balance and update that balance here. Else we return negative and also update that false here, right? So we do this recursively for the whole node. So the stack, we go stack by stack, going node by node, and returning set value. And after all said and done, if this returns true at the end of the day, then we are golden. Else, that means at one point or the other, it must have found a place where the height of the left node and the right node did not meet this situation right here. And if it does not meet and return the truth or true in this situation right here, then we have a false, and hence what we are printing out, right? And you will see how here we say is balanced, or we pass in the node, and we pass in what do you call it, and then we pass in the the either true, because we're trying to find either true or false, right? So we are passing in this guy. So after we found it, we want to collect the index of 1. That's the value we are looking for, either true or false. That's the one we're interested in. So we check that one if it's true or false, and we get our value. So from that point, we can then look at the algorithm pattern, and we could see that this is a post order transversal, right? This algorithm pattern is a post order transversal because we have a left node call first, analysis first, a right node analysis second, and then we take the node analysis third. And that's why we have a name post order transversal. And then we then look at the time complexity. What's happening? Every node is being visited at the end of the day. After every, after all the stuff we will do, we'll, sorry about that, we would have to, visit every single node in the tree. And that's an O of n time because every node is visited. And then space. We're looking at the recursive, what do you call it? The recursive call, or the stack, right? Now, at every stack, we have analysis of the tree, right? So that will give us an O of h, which is the height of the tree. Now, because of stack, right, this I believe would give us a space of O of n, if I'm not mistaken, because for every time we call a new stack where we go to a list, and we analyze that list or that node. Every time we go to a node and we analyze that node, we basically do what's it called? We basically hold a get height, we basically hold the balance, and that is going through the entire list. And so yes, that holds our complexity because every node is visited by recursion, right?